Okay, so good afternoon. So back with the Cosmo BPHC seminar series. So today one of the PhD scholar from the group, Ameya Kolhatkar, will present his research work, the Amplitude-Growth, Degeneracy and Implied as Diagnostic for Background-Inert Modified Gravity. So Ameya, the stage is yours. Now you can start.
Okay, thank you so much, sir, for giving this opportunity. Happy to be the fifth speaker in this Cosmo BPHC seminar series. And today I'll be talking about the, as sir said, Amplitude-Growth Degeneracy and Implied age diagnostic for background-inert modified. So let me just give you the prelude. So this work is based on the recent preprint, and we observe that attempting to constrain a background-inert perturbative coupling, let's call it lambda, using late time probes gives us a degeneracy between this lambda and the clustering amplitude sigma HZ. But this in turn is a deeper degeneracy between the primordial amplitude AS and the total unnormalized growth B0. So models that employ this lambda seem to have statistical preference over their vanilla or lambda counterparts, or even over lambda sigma. The cause is simple. The cause is that late time probes often leave AS unconstrained, and this makes it degenerate with D0, as we see. This degeneracy, like I said, is propagated as the sigma H0 lambda degeneracy. And the simple fix is we use the constraint on log 10 to the 10 ES as a Gaussian prior in the analysis. So we observe that at least in this case, the statistical preference dies out and lambda CDM is moderately to strongly favored. So since the work is about FQ gravity, I'm pretty sure all of us are, maybe there are some people who are not familiar with it. So let me ponder upon 1 or 2 minutes. So the action is given by equation 1. And this is built out of the non-metricity scalar, which is given by this Q. And this Q is itself 6 square inch spatially flat FLRW metric. And the important thing to note is that when FQ equal to Q, this is just GR plus some boundary term. Right? So this R, circle over R, represents the Ricci scalar in the Levi-Civita connection. And this is just equal to this Q plus some boundary. And again, in spatially flat FLRW case, we have the Friedman-like equations given by 2 and 3, where Rho D and PD are given by equations 4 and 5. So now there is something special about this root Q, and it is quite obvious if you see that since Q is 6h square, root Q will be a boundary term, which is just the total derivative of root 6 times log A. And this is special because under this shift of FQ goes to FQ plus this lambda naught root of Q naught, the rho and P retains its form. So essentially this root Q does not propagate any energy density or pressure. And this is what makes it background inert. So now note that this lambda 0 only enters to the perturbation sector through this mu g. So mu g is nothing but the ratio of the effective gravitational constant to the Newtonian gravitational constant. And in the quasi-static approximation, this is just equal to 1 by fq. So this f sub q is dfq by dq. And this is scale independent. And this is nice for reasons that will be discussed later. So let me digress a bit and talk about strong coupling issues. So recently, I mean, not that recently, in 2024, a PRL paper showed that all FQ branches have either strong coupling or ghost issues for the spatially flat FLRW case. And they identified that the only non-problematic or only pathology-free Lagrangian that you can write is FQ equal to AQ plus B, which is just GR, or rather lambda sigma. Hence, it is important to note that the models defined here are a purely phenomenological work, and a more considerate treatment of maybe EFT analysis or deeper perturbation analysis is required. Nonetheless, this is a problem, and even though we are doing a phenomenological work, we define this proximity parameter given by equation 8. It simply measures how far or how close our theory is when compared to the pathology-free boundary, which is epsilon equal to 0. Now, epsilon equal to 0 is a pathology-free boundary because, as we noted, this linear form AQ plus B will give FQQ equal to 0, which will mean that the theory is pathology. So it's a heuristic treatment, and this is not a substitute for any full perturbation analysis. Coming to QSA, which is the quasi-static approximation, we see 3 curves here. Now, the maroon curve is corresponding to 0.1 per megaparsec. And this gives us around 0.001% of 1, which is the top line here. Now, this line is basically AH by CK square equal to 1. And this measures the whether we are in sub-horizon limit or super-horizon limit or what. So in order to be in super-horizon limit, sub-horizon limit, we need this value to be much less than 1. So for these two maroon and navy curves, we have both of these cases to be much less than 1. And this dashed green curve is something which is within 10%. So around 10% of 1. But problem is that this green curve corresponds to 0.001 value per megaparsec, and this is much higher than anything what LSS goes. So typical scales would be around 0.1 or 0.01 is maximum. So that gives us 0.1 to 0.01%, and that is fine. So let me restrict the theory classes further by imposing 2 conditions. So one is that the expansion history of any model that you choose should be lambda CDM for all redshifts greater than recombination redshift, which is around 1100. This is nice because it preserves CMB or sound horizon, angular diameter, distance, and damping scale. And second is that the perturbative coupling lambda only enters through the linear perturbation sector given by equation 9. And this mu g is the same mu that we saw a couple of slides ago, where this is given by 1 by FQ in our case. But this also has to converge to GR for very high redshift. So this ensures that whatever theory we are using, it converges to lambda CDM like behavior in background as well as perturbation case. Okay, so the AS D0 degeneracy can be explained as follows. So you begin with the normalization of Planck, normalization of the power spectrum as given in equation 10. And for scales corresponding to 8 H inverse megaparsec, you have sigma 80 given by the sigma 80 square given by equation 11. And notice that this D0 comes out of the integral. So this D0 is not it's not scale dependent, and hence it can come. Now this will depend in general on theta. Theta is nothing but this omega m0 omega b h square multiplied with both ns and h. Now equation 11, you will see it's invariant under a rescaling. So this rescaling is just rescale AS to C, some phi square AS and E0 to E0 by phi. And this is nothing but the AGS D0 degeneracy. Now generally what happens is when you use a full Boltzmann treatment, this AS is also fixed. So when you have an anchored AS, when you have an anchored primordial amplitude, there is no scope for this phi to vary. But if you use just background probes or probes which do not constrain AS, this phi square AS remains free, and the sampler will absorb this phi in growth and this will propagate the inflation in sigma h0 through this equation in the. So this is how the AS D0 degeneracy becomes the sigma h0 lambda degeneracy. So we identify some instances of this in the literature. So a 2020 paper by Barros and others uses two models with lambda root Q coupling and find higher sigma h0 values for a non-zero coupling. Athaide and others use various combinations out of the CMB likelihood from Planck 2018 with the following Lagrangian, and they find that they find similar values for sigma h0 as opposed to inflated or deflated values, and this is simply because they use MGCAM. So MGCAM is the full Boltzmann solver which will fix AS, and hence you do not see that. A very recent study by Lee and others use only RSD to probe the M root Q coupling in 3 different FQ models. They find an inflation of sigma h0 for a non-zero M, and they also find the lower chi-square mean. So then I said that the fix was the Gaussian prior of this log of 10 to the 10 AS. But how do we actually use it? So in order to probe this degeneracy, in order to probe this invariance, we use a reference model, which is lambda CDM, and this will give us this equation. So sigma h0 reference square will also give you the same equation. And you can tabulate this using a Boltzmann solver like CAM or class over theta. You take the ratio of the two, and after taking the ratio, you just take the log, and you have this equation 12. This will give you what AS implied is. So AS implied is nothing but whatever answer your sampler gives regarding sigma h0. This AS implied tells us what will the primordial amplitude have to have been in order to give you that clustering amplitude today. Okay? So in case of lambda CDM, you might have something like, let's say AS is pretty much constrained by Planck. So this will be 3.044 plus or minus 0.0, something like that. And it will correspond to a sigma h0 amplitude of 0.78 or something like that. But the instance of the degeneracy that we saw just now, it will cause the sigma h0 to inflate and basically give you a higher value of sigma h0, like around 0.83 or 0.85. In some cases, it will even reach 0.9. So even though you can't say that it is unphysical because you don't expect it, you could calculate this quantity, which is AS implied, and then see how far it goes from the actual Planck value. Now again, this I of theta, which was the integral, that cancels out because for same theta, due to the conditions that we imposed, the transfer function will be identical, and hence this integral will also be same. So that will cancel out. So you see how this becomes computationally inexpensive. And the last thing to note here is that this lambda, which is the perturbative coupling, it only enters through the total growth. So if for some reason you don't include this last term, you will have no probe of lambda whatsoever. So there are two models used. First is lambda CDM, which will be this. So this is just, if you just discount this lambda 0 term, this is just lambda CDM. And when you include this, you have equations 13 and 14 giving you the expansion history h of z and the effective gravitational coupling mu. And this is given by equation 13, 14. And the hybrid model, it's very, I mean, it's not very widely used, but it has been considered in the past. So it is given by this Lagrangian. And the following expressions corresponding to it are given by equations 15 and 16. So about data and pipelines, we use two distinct data pipelines with the following base combination, which is compressed CMB plus EG plus Pantheon plus. The first one is BD2R, which we call BD2R, which is base plus basic DR2 BAW plus RSD, and BHDP, which is just base plus SGSS 16, DR16 BAW plus. Now, BAW plus includes covariance between the PAO points and F sigma 8 points, while the case 1, which is BD2R, just has separate points for both of them. Now, something to note that both RSD and EG compilations are taken from this LSTAS paper, and they contains 2 points from Viper's BD2R catalog. We remove them from the EG to avoid double counting and statistical contamination. And I'll maybe spend 2 or 3 slides on how it can become a disaster if you don't discount that. Now, for sampler information, we are using nested sampling for reporting log evidence. Chain visualization is done by getDist, and the tabulation is done by CAM. Now, all 3 of them are available in the publicly available code, which is Cosmix. So Cosmix is our own custom code, and you can check it out on the GitHub link. So a word about the prior. We use this, as I said, we use the constraint from Planck 2018 as a Gaussian prior. And this is applied on the derived quantity AS implied for every likelihood. So the reason why we tabulated this using CAM is so that we can use it to apply on every likelihood call. And this constrain the join vector sigma 80 lambda naught and all these things. And this breaks the degeneracy. So just for notational ease, I'll be using in all figures, I'll use log AS instead of log 10 to 10. So these are the contour plots. So you can see that in compared to the vanilla models, which is the gray and blue curves, which are barely visible here, when you include the lambda naught coupling, the curves inflate. So the curves become bigger, much bigger than what their counterparts were. And you see a peculiarity where you have this green and yellow curves where these are huge as compared to the other curves. Now, there is a positive degeneracy, so positive correlation between sigma 80 and lambda naught in both cases. And when you apply the prior on AS, rather log 10 to the 10, this flips the correlation to a negative correlation. The contours shrink and you get a much tighter 1 sigma constraints. Now, this would tell us that the degeneracy, this would tell us that the prescription that we use to fix the degeneracy has worked. Because instead of the sampler using this as a ridge to slide along, it now has to choose between compensating either lambda 0 or sigma 8. One more thing to note is that in both cases, as soon as you apply the prior, it goes from having this positive non-zero value of lambda naught, and it goes back to giving some being consistent with lambda naught equal to 0. Rest all quantities are almost same for all cases, but the only ones important here are this lambda naught and sigma 8. Now this, okay, so ICE is just information, criteria, and evidence. It's short for that. And you will see that for lambda CDM, this is 0.794. When you add lambda naught, this goes up, shoots up by 0.853. And when you use this prescription of LNAS, it returns back to almost the same value. Importantly, look at the error. The 1 sigma error also shrinks down by a factor of 2. Now, this is also the same in the hybrid model case, where the 1 sigma constraint goes higher, so it is inflated in both cases, and it again shrinks back with a much tighter error on it. So same is for lambda naught. So lambda naught will give you 0.67. So this is somewhere offset of 0. But after the fix, you have lambda naught becoming almost corresponding to 0. Same for this case. And this is also same for the SDSS pipeline. One thing to note, evidence and information criteria wise, is that in this case, if you just focus on the plus lambda 0 columns, in both of them, AIC, delta AIC is minus 0.5. Here it is minus 0.7 for delta DIC. Here it is plus 0.5 and this plus 0.2. Whereas BIC and log Z are giving opposite inference. So delta AIC and delta DIC is in the inconclusive range. Delta BIC and delta log Z are both in the weakly disfavoring range. Now, immediately when you apply this prior, you see that this AIC, this is still within 2. So this is still within the inconclusive range, but it is pushing to the boundary of weak disfavor. DIC goes even further. In this case, it goes much higher. And here evidence is also much, much higher. You get a similar kind of treatment when you see the other pipeline. So let me talk about cosmic evolution. So on background, you see that Q of Z and omega effective, both of them follow a nice phase transition from deceleration to acceleration. And this happens somewhere around 0.67. Same for H of Z and mu, which is the distance modulus. So we see that these background probes, including F sigma 8, these background probes and this expansion history, all of them cannot differentiate between the vanilla and lambda naught variants. If you look at the F sigma 8 plot, you see that these curves are somewhat, for one point, they are a better fit. So for high Z, they are somewhat better fit than our models. So this is the sampler, this is the active case of sampler trying to use that degeneracy to find some kind of statistical preference for data. If you stop the analysis here without invoking this implied A subscription, you would conclude that you have some inconclusive evidence for lambda not equal to 0, and you would need stage 4 or stage 5 data from LSST and other probes to discriminate that. And you would say that the higher sigma 8 0 is the prediction of the FQ models or any theory that is. But the full story reveals itself only after using the AS diagnostic, and this reveals moderate to strong evidence against all FQ models as agreed upon by all comparative models. So again, you see that in these tables, you see AIC, DIC are favoring in somewhat either in the inconclusive range, or either they are favoring the model very mildly, and BIC and log Z are mildly disfavoring the model. So there is some discrepancy between the statistical evidence metrics. But again, when you use that prescription, that goes away. All of them agree, and you have disfavoring over all models. Now you can see the perturbation sector. So this mu G you see for plus lambda naught variants, this gravity is suppressed much, much higher. So this suppression is much higher, and when you use that prescription, it goes to much lower value. So this is mild, much mild suppression. So this is the implied AS quantification. So you see, first, when you consider normal vanilla models, maybe any pipeline, these give some AS. Okay? So even our vanilla models are not, since we are using non-CMB data or other background data, we are not using any kind of probe to fix AS, and hence there is some sort of discrepancy between this. But when you actually see that when you use lambda 0, when you use this background inert coupling, that AS needed to produce such a high sigma goes up. It shoots up and it goes from, let's say, 1.5 sigma to 1.7 sigma in the BD2R case, and 2.3 to 2.6 sigma in the BSDP case. Now, of course, when you use that, it sits very nicely in the 1 sigma contour range. So now the answer that you would have is much more consistent. At least we believe it's much more consistent with the full CMB treatment. Okay? I'll come to that later. Now again, this strong coupling boundary. So this strong coupling boundary is it's just a plot of epsilon SC, and you see that the actual proximity to this dotted line is only for the recent redshifts. So for all redshifts higher than maybe 10 or something like that, you have a rapid fall off from these models. So I said that you should exclude the double counting, and here is why. So if I had not excluded that double counting, what would have happened is that I would get much better, sort of much well-behaved evidence metrics. And interestingly, for the BSDP case, you would get some kind of residual evidence. And you would get AIC and DIC would prefer this model a lot. So naively, you would think that whatever this model is, it is much better than lambda CDM, and it produces a non-zero lambda naught, and it even has evidence. So even after fixing the problem that degeneracy gave, you would think that this is evidence, but this is purely a fact due to double counting. And this can be shown by pool plots. So this pool plots is nothing but the residual. So this residual will be, as you can see, this is the double counting point. So this one and this two. These two pull the much higher than the other points. Again, in RSG also, when you see this 1 point, I think this is 1.48. This is also much higher, and these are the same points which you remove. Okay, so nearing the end of my talk, so let me come to the scope and applicability of it. So the two conditions restricting the theory class are sufficient for the applicability of the implied diagnostic, implied AS diagnostic. It can be applied for theories without any anisotropic stress. So general NG parameterizations have mu equal to 1 and, sorry, mu not equal to 1 and gamma not equal to 1. That is basically so gamma is the ratio of the two gauge potentials. And this can be tested for theories outside the FQ class as well. This has not been done in this work, but I mean, somebody could try. The compressed CMB and implied AS diagnostic as a whole presents as a computationally inexpensive alternative to the full Boltzmann treatment. So somebody who has run CAM or class in the past would recall that it's extremely expensive. You need to run the code for a long time to give this. And if you are using late time, the belief is that compressed CMB is sufficient. And there are many papers on it. But for classes of theories which use background-inert perturbative coupling, this, as we saw it, at least in FQ case, it falls off. Whether or not this is applicable to a much larger class of models is something to be discussed. So conclusions are pretty straightforward. We identify the degeneracy implicit with using a background-inert perturbative coupling in FQ gravity. So there are a couple of caveats here. So caveat number one is that this is done in a phenomenological way, as we said, in order to, in absence of any strong coupling fix. So such a theory can be identified to have degeneracy. We lay out a minimal condition for the models and for the applicability of the degeneracy. So the model must satisfy both the convergence to lambda CDM in both background as well as perturbative case. And we proposed a fix. So the fix is nothing but the Gaussian prior, which is the constraint, 1 sigma constraint on log 10 to the 10 ES, which is given by Planck 2018. So future outlook is an actual comparison with the full Boltzmann treatment. So you would like to see the same models run through maybe CAMP or class or any other Boltzmann solver to see how much the results actually differ. Interestingly, we would also like to check how this extends to theories beyond the gamma equal to 1 class. So we would see how this behaves, and maybe if we can prescribe some conditions and some fixes for theories of class outside gamma equal to 1. And also, lastly, we would like to test things other than FQ. So if this is in some other theories which are other than FQ but fall under the same category as the conditions given above, it would be interesting to see. Okay. So with that, I end my talk, and thank you for listening. And if there are any questions, then I'll be happy to take them.
Thank you, Ameya. It is a nice talk. So, any queries or questions?
Yes.
Yeah, Simran, you can.
Hi, thank you so much for your talk. So, I was wondering, there is some omega m naught you mentioned in the slide 8, and also you mentioned about omega b0, right, for the baryons?
Right.
Yeah, yeah. So, what do you mean by this omega m0? Is it cold dark matter or it's a total matter? I mean, since you mentioned omega baryon as a separate one, so what is this omega m0 here?
Yeah. So, okay. So as you might know, compress CMB uses
Yes, yes,
NS and omega B.
yeah.
So this omega m0 does represent total matter. So it's dark matter as well as baryons. But
But
yeah, but maybe
yeah,
I should not have written omega m0 here, since omega B is already here.
yeah,
It's a double
exactly.
double
Yeah, double
outcome
kind of
condition, right?
yeah, 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 yeah.
Right.
That's what my doubt was. And also, one comment might be you mentioned about the degeneracy. So I see
Yeah.
that your sigma 8 values are very higher. I mean, it's going beyond 0.85 or maybe 0.9 for some cases.
Yes.
So I see that this might change even the meta density if you have some higher sigma 8 or something. I mean, a suppression on in sigma 8. So what do you think? I think there might be some degeneracy for omega m naught as well.
Yeah, but omega n naught is pretty consistent, right? So here also you see it is around 0.304, 305, even here. So omega n naught values are not touched because they are, uh, as far as I believe, they are constrained by the background probes, which is like BAOs or type 1 SA, type 1 SN. So if you only use RSD or compressed CMB, which actually probe the perturbative sector and give you sigma 8,
Yeah. Yeah.
only those will, so in that case only you will have some degeneracy.
That's what. So how did you calculate sigma 8 here? You might have used some RSG data here, right?
Right. So in this case, here for this pipeline, you have RSD. It's a secondary comparison. It's not full shape analysis or anything. But
Yeah.
for the SDSS case, so SDSS DR16 BAO plus gives you joint covariance between BAOs and RSD.
Okay, yeah, this only. I saw that there is 0.9 value for lambda CDM plus
Yes.
lambda naught. So it's a much pretty, I mean, it's a higher value than we expect as we consider for the lambda CDM.
Yes. Yes.
And
It is much higher.
so I think there might be some degeneracy when when you have this higher value, then there might be some degeneracy in other parameters, maybe. So I don't know. Okay, let's see. Thank you.
Yeah. Yeah. Okay. I mean, about degeneracy, you see that this maybe that is what I was saying, that this if you stop at this analysis, then you would think that this is the prediction of sigma, this is the prediction of your FQ models. But if you use this description, then you see that it returns back to normal. It gives you back the plant values. So in this column is the should be the final result.
I
So
see.
here also, yeah. So here also you see it is lower than what lambda CDM predicted as well. So it is anchored very tightly towards Planck values, and this is why you would not. I would say you should not trust. I mean this 0.90
Right,
because in
right.
my
That's what.
opinion it's incomplete analysis. Right? Yes.
Yeah. Okay, so you used compressed CMB in your case, or it's
Yes.
just okay, okay. Thank you.
Yes. Father.
Hi, Ameya. Nice presentation and very nice work. So my question is based on like not question. My doubt is based on this information criterion.
Okay.
Where when you compare your model FQ model with lambda CDM and any data set, there it is fitting nicely to the lambda CDM model. But when we are taking the statistical comparison tools, why it is heavily penalized? Like, what is the reason? Basically, these tools also use how nicely a model is fitting to data, right?
Right.
So why so? Like, why it is coming like that?
So you are saying that these curves are almost overlapping, but then statistically they are not very nice. Is that what your
Yeah,
question
yeah,
is?
yeah.
Yeah. So I think this is just that it is like if you know AIC is just your chi-square minimum plus 2 times free parameters. So if you have additional parameters, then it will penalize you if it does not improve the minimum chi-square by a higher amount.
So can we say that in that curve, just our mean value is fitting nice to lambda CDM, but if we consider our complete result or if we compare with the equivalent form of lambda CDM, then it might be deviating. Like
I
if you are
think,
taking the whole 1 sigma, 2 sigma value.
yeah. I mean, there is 1 sigma, 2 sigma value in the residual.
Right. Okay.
But I think, yeah, I think the issue here is that we are comparing two different things. So we are saying that, so this is H naught, so this is at Z equal to 0. But such values are obtained at all redshifts. So at all redshifts, you have similar values. So how H naught is similar in all cases, you have same thing for all redshifts, and hence you see a similar graph. So I don't think the graph has anything to do with AIC, BIC, or I mean any evidence metric.
Yeah, but if we in some graph we also compare with the error bars, right? So we
Right.
see that our curve is nicely fitting to the data, but this statistical comparison which use how a model is fitting to data, that is the
Mhm.
fundamental behind this statistical criterion, right? And why that doesn't come right? In on what basis it is getting penalized? That is my question.
As far as I understand, it penalizes on the base such that when you try to fit it with the data in order to achieve a superior fit, how many parameters are you using? So there has to be some kind of balance between the two. So maybe you can come up with I mean, anybody can come up with a model which uses 100 parameters and fits the data extremely well. But then I think that is based on the Occam's razors or Occam penalty, where you would like your model to be as simple as possible and explain as many things as possible.
Okay, okay. Thank you.
Santh?
Yeah, Ameya, very nice talk. So I just had a small theoretical question. So when you are taking the first, that K, like the co-moving wave number, I guess, so 0.01 or something like that, the maroon and navy blue, etc.
Yes.
Yeah, in the first slide. Yeah, yeah, something like that. So when we typically put it in, like I think in the Boltzmann code, etc., it's typically assumed that AS is like something like 2.1 into 10 to the power minus 9, like from the covenant normalization.
Yes.
And but the problem is that there is also a pivot scale, right? I mean, for 0.05 kilomega per second hertz. So I'm just saying
Right.
that if you take, I mean, again, you probably use the smaller one, but I'm saying that if you take that AS is changing, I mean, based on your background one before even the CAM one, I think you haven't taken too much about the pivot scale, because if the pivot scale also changes, then the linear perturbation itself breaks down, right? I mean, I think that is something somewhat missing. I mean, maybe you have assumed that the K would always be inside the horizon, so it doesn't matter. So
Right.
I'm just, could you just comment on that? Yeah.
Yeah, I mean, you said it yourself. So that is why there's such a emphasis on being sub-horizon. So in the quasi-static approximation, you could not really think about those things.
Yeah, but the point is that the AS is also increasing, right? I mean, so for example, if you take the matter power spectrum, when if the AS keeps on changing, the pivot school also would change in order to make sure the SDDSS data is consistent, right? So that's what my concern is. I mean, if you have a fixed, how should I say, a cutoff scale like 0.05 megaparsec, that I understand. But as because in your model, the AS is inherently dependent, it seems like in order to make it observation, the cutoff scale would also shift a bit, right? So in a sense that whether the quasi-static approximation is valid or not, that's what I was wondering. I mean,
But
again, this is just a
AS
technical question, but yeah.
Yeah, but AS is not dependent on anything. That is the whole point, right? AS is not dependent, it is unanchored, and that is why we get this problem of degeneration.
Okay. I see. So in a sense that, okay, irrespective of that, so in a sense that the anchor K star would always be more or less fixed, right? I mean, so in a sense that there is not
Yeah.
much problem on that, right?
Yeah.
Okay. Thank you. Very nice.
Okay, Ameya. So thank you. We'll check another speaker for next talk. So thank you all.
Thank you.